Thank you very much, Chuchu, for this introduction. So if my voice is okay, I go ahead, because this microphone only records for the recording. And if you feel I need to speak louder, just let me know. So just to get started, like Chuchu mentioned, I got my education back in Armenia. And when in 1998, I got the opportunity to come to Georgia Tech to work for Aerospace Engineering Department on stability flight control systems, this is how the aerospace industry was presented, through powerful, consistent, safety-critical, large-scale, super expensive technologies. And these 25 years I kept working in this country, the industry evolved towards more small-scale, autonomous, human-centered, intelligent technologies, reaching out to consumer markets like agriculture, emergency response, and many others. This was driven by the data revolution, I guess, because the CPUs and GPUs became cheap and available. That promoted lots of developments in machine learning community, in computer science. Some of these scientists reinvented control methods within their own disciplines. And the landscape overall for our research changed fundamentally. This has become a new reality for us. So what did we observe coming from computer science? We observed very impressive empirical demonstrations. The animation that you see on the left of a humanoid robot falling, collecting data, learning, falling again, collecting, learning again, over a few months gained more than 10 million views on YouTube. The cubic Rubik, or that kind of vision-based navigation in complex terrain, everything just proved the fact that many of these machine learning methods work very well empirically. And yet, on the other end, we see some of the accidents that have costed human lives. So there is a big gap here, what's possible and what's provable and what's guaranteed. And obviously, when we deal with safety critical systems, we have to keep in mind that collecting safely large amount of data and using it in real-time online applications, especially when the vehicles are operating at high speeds, can be just dangerous and not possible. And the accidents can be catastrophic, deadly, cost human lives. That's why the safety must be guaranteed by architecture. So keeping this in mind, let's see what do we have. So we always have these complex dynamics, uncertain models, uncertain environments. On one hand, we have control theoretic tools that are ideally serving the purpose of structured models, parametric uncertainties, deterministic representations. On the other hand, we have data-driven machine learning tools that are good for general models, less restrictive assumptions, unstructured uncertainties, stochastic representations. So safety and robustness on one end are guaranteed within very conservative setting quite often. And on the other hand, the empirical performance is just irresistible, right? You get attracted to achieving this type of performance level. So how to bridge the divide? This is what our work has been focusing over the last few years. And thank you for having me here. I'm happy to go over it. So let's go through typical data-driven control pipeline. Given a system, so we can collect its data through some data logging policy. Then we build a regressor using the data. The regressor is used to derive an optimization algorithm to come up with a control policy that gets applied to the real system. This data-driven control design pipeline is obviously distribution dependent. The data logging policy depends upon the system, and our data logging policy, which depends upon the sensors available, how frequently we would like to sample, and other laws that we will define dependent upon the particular application. Data gets characterized by distribution, so we get a training data and characterize it by some distribution that's used in building the regressor model, and then there is the optimization that produces the control policy. When we get to apply to the real system, here is what happens. So we minimize an expectation based on training data that helps us to achieve a control objective. But when we apply to the real system, there is always distribution shift. And the distribution shifts can be characterized by two types of uncertainties, epistemic and aleatoric, the way they refer to it in machine learning community, where epistemic pertains to system uncertainties, modeling uncertainties, and aleatoric are the environmental uncertainties that we have less control over or no control. So these distribution shifts render our control certificates invalid. Our control objective may not be met. So we're interested in robustness to distribution shifts. So we want to be robust to both epistemic and aleatoric uncertainties, and we want to be able to quantify the distribution shift. So we want to make sure that we can have ambiguity sets around the training data so that the true distribution during the operation of the system always lies within a known ball. And we want to be agnostic to the training data so we can mitigate the distribution shifts and we can control the size of the guaranteed set so that the control objective can be valid within this ambiguity set. Why is it important to have distributional robustness guarantees? It can give us the opportunity to do safe predictive control. This type of language is our natural ability to consider epistemic and aleatoric uncertainties, and systems and our understanding of them truly have to be stochastic. And the design principles for these distributional robustness guarantees can help us to merge the design space with the test space. Talking of aerospace industry again, if we talk of the flight controllers deployed on big airplane, they are obviously designed in deterministic setting around a large gain scheduled flight envelope. There are robust adaptive augmentations, the gain and phase margins are checked, tested in Monte Carlo simulations where there are uncertainty distributions that are stochastic in their nature. To merge the design space with the test space, our research can play a pivotal role. Distributionally robust control is not new. There is a rich literature here under certain set of assumptions when the system operates around data that's close to its training distribution. And there are different types of control problem formulations, either in path following setting or in cooperative setting. I don't want to go through the details of this. I just want to focus quickly more on our research. So what's the setting? As I said, we have a regressor that's built from the training data distribution. It's optimized for a control policy and it gets applied to a true system that during its operation faces data that might have not been used in the training distribution. And we have distribution shifts. So what we want to have some type of robust adaptive augmentation here that can help us to mitigate the distribution shift. We can be distributionally robust and also predictive. Here is where we'll be using our L1 adaptive controller that I had the opportunity to present at MIT twice over the last maybe 2 decades, or maybe 3 times, once also online. I'll just go briefly through it. L1 adaptive controller is a type of control architecture where the estimation loop gets decoupled from the control loop through a low pass filtering structure, and it helps us to have a priori predictable performance and robustness guarantees, and to tune the controller systematically. So the key feature of the architecture is the decoupling, and it helped us to transition the control technology to different industries, including Raymarine Evolution Autopilot, hydraulic pumps of Caterpillar. We tested it on experimental rig in Statoil and to many other aerospace applications and different industries. I won't go through the list now. So the key idea is the decoupling of estimation and control loops that subsequently leads to decoupled performance bounds, one of which is inverse proportional to the rate of adaptation and the other is proportional to the low pass filter bandwidth. So the architecture relies on decoupling of estimation and control loops, while the analysis relies on small gain theorem and Lyapunov stability theory that have long history of being well-exercised methods, well-established methods for provable certificates in safety-critical systems. We first came out with the L1 adaptive controller back in 2004-05 when we were trying to address some of the pressing challenges that model reference adaptive controllers had, and we got the opportunity to test it for NASA's subscale 757 5.5% model at NASA facilities known as AirStar model. We were able to hold the aircraft in stall and post-stall conditions. Subsequently, it led to lots of collaborations and joint papers with Raytheon, Boeing, and many other companies. As I mentioned, commercialization efforts. We worked also with Eurocopter on testing it on their helicopter model. Transition efforts. In 2015, one of my former students called me from test pilot school at Edwards Air Force Base, offering us the opportunity to test it on manned aircraft with people on board. This is where the pilots get trained to get license for piloting aircraft. So this was already a completely new milestone with a different level of kind of serious approach because we were going to have people on board. But these variable stability jets have the opportunity to shut down any dangerous maneuver and recover the safety of the aircraft by reverting to nominal design. And this led subsequently to safe learning and control and distributionally robust control. So as I said, this is the Learjet platform that we were given in 2015. From the left, the 2 students are my students, the rest are the flight test team. Just to give you a brief idea how these experiments happen, sometime in September we get the model with the flight test schedule being fixed for March. In November, the controller goes into freeze for autopilot compilation till March. In March, we have 2 weeks of ground run testing before 1 week of flights. So this is pretty serious, and during the 4 months of preparation, we're having long, like 10-hour calls bi-weekly with Air Force team, and some marshals have to sign some paperwork. So we get approved to test accidental scenarios where we can show that we can recover for safety. We got some press out of it. Aviation Week wrote about us. We got the F-16 Vista aircraft, which we were not allowed to publish or show. And in 2018, we got our last opportunity to try, after which the COVID hit, because these tests were happening only biannually. So I'll just show this flight test. Let me see if we have enough voice. So in 1967, there was an accident where luckily the pilot survived. This accident data was available to load on Learjet to force it mimic like this accidental scenario, and to see what happens to the aircraft. Can the pilots control it? If they cannot, the variable stability system shuts it down, and then they put the L1 adaptive controller to test for the same data. And you will hear here the pilots saying something is still left, and that something is still left we were able to recover with the stochastic analysis and find the answer to it. Now listen to pilot's audio. I hope we have audio here. So pilot lost the control, the VSS shut it down. Now they go into the same scenario with our controller.
Hey, test in 3, 2, 1, now. So you can feel there at high frequency, but some high frequency inputs excited the roll. What frequency the roll overshoot or oscillation density is less. Okay. There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good at pitch. All right, I have the different complete.
Now they go into engine out scenarios, and without pilot, with pilot, and with our controller. There is bank angle degradation on the right of the screen.
Okay, power coming back. My hands up for 3, 2, 1, now. Controls fixed. And recover. And recovery. Power back.
I'm ready to try this now with a pilot correcting for it. So,
Okay, and I'll give it about a 1 second reaction time. I'm on conditions.
and then recording on my call. Ready, power.
Okay, power, the left throttle. Okay, in 3, 2, 1, now. More potato and recover.
And I'm recording off.
Here, bring off magic throttle.
Okay, I'm ready for the recording on ready, power.
Okay, left throttle coming back in 3, 2, 1, now. Not touching the controls. Nice demonstration. Yeah, check that out. About 3 degrees of left bank. Speeding in the rudder match. I can feel it. It is the cynical difference. Yeah, just sending a bit, but that would be easy to compensate for. Yeah. Okay, I think you got some good data there. Matching power for you.
So 3 degrees were left, and our stochastic analysis helped us to find out how this left. So we were on the front page of aerospace and defense science technology. Actually, for this one, I wasn't interviewed. For Aviation Week, I was always interviewed, so I got the message from the College of Engineering. It was great to see that the work could have impact for critical technologies. With lots of other applications. So, for example, this one is the one that put us into New York Times, like elderly care, and the focus here was on integrating human perception of safety, because engineering safety, it's about collision avoidance, but human perception of safety is different. And the elderly care industry is just growing because people now live longer and there aren't enough young people to work in nursing homes. We use virtual reality technology to test people's perception of safety, which is a lot more conservative than the actual engineering safety defined by collision avoidance. And this Cinderella cartoon was our inspiration of thinking of small technologies that can be ground robots, it can be flying drones, to help humans. This was, of course, very futuristic, and that's why New York Times captured it. So they called friends for cooperation because it's increased payload. These are all communication control problems. And then there is the question whether she feels safe in the presence of robots. This is an experiment that was done actually in University of South California. So where you see the dog running with a 3 kilo weight and falling apart, and here they are adding the L1 controller, and I think, how does it run? So I'm not able, here it is, it's woke up, took a while, and it runs with 5 kilos and is not falling apart. And we are not part of it, so it wasn't done in our lab. They just shared with us, and we were happy to see and use it. But then in 2018, I get invited to Georgia Tech, like I'm invited today here. And during my meeting with Evangelos Theodorou, who was one of the finalists of this Lockheed Martin and MIT setup Alpha Pilot competition, he asked me if we could bring the L1 adaptive controller to this environment. And it was immediately clear that we just can't do it without extra work, because all I showed up until now, the path was defined and we were following. It's the big airplane flying, big flight envelope, or any other application we did, the path is predefined. Here there is continuous learning that has to happen, finding new ways, continuous replanning, and in this environment, obviously, it was not clear how to bring L1 and to make sure that it works. So if L1 adaptive controller has provided certificates of performance and robustness in the sense of classical control, transient performance guarantees, steady state performance, time delay margin, and disturbance rejection. For these new environments, as the world around it changes, we need new forms of guarantees, and we need to be appropriately defined for data-driven systems with stochastic representations and have distributional guarantees. So this brings me to the outline of today's talk. So the first thing naturally that we did, we worked with Georgia Tech to bring L1 to their system. And they had MPPI, which is like Model Predictive Path Integral Control. It's the model predictive control with a learning component. And we tried to put L1 there to see if we could clear more gates by getting better tracking. And we did it empirically solely. Then the question comes up, if we're flying in these cluttered environments, will the baseline gain scheduled linear controllers be appropriate, or we need to look for new type of nonlinear controllers that would be appropriate for cluttered environments? This brought us to control contraction metrics and contraction-based controllers that would give us a new class of nonlinear baseline controllers for these cluttered environments. Then the question comes up, if we do this deterministically, can we add learning to it to make sure we can be even more sophisticated? If we learn the uncertainty and reduce the amount of uncertainties, we can guarantee better tubes for more precise performance. And that brought us to defining a new framework for distributionally robust adaptive control to get predictable performance in terms of certificates for distribution shifts and close the language barrier between data-driven machine learning control and robust adaptive control methodologies. Now, one by one, going to this model predictive path integral controller of Georgia Tech. So we augmented it with L1 adaptive controller to get the guarantees for better tracking. So what does model predictive path integral control do? It's a method for fast and safe replanning. So given an uncertain system, and they formulated it in discrete time, the model predictive path integral controller is an optimal control computation forward in time for nominal system, and it updates the control sequence iteratively by sampling thousands of trajectories. So L1 adaptive controller was compensating for the discrepancies between this nominal system and the real system. There is an opportunity to leverage parallel sampling for modern GPUs, and we can handle complex, possibly non-differential dynamics and cost functions. This paper was accepted in IROS. Here is that simulation environment, and this happened in the year of COVID, 2020. Getting into lab and flying anything like this would have been impossible, but luckily, I mean, this simulation environment kept everyone busy and happy to work on the exchange. So we cleared some of the gates that were not cleared by the MPPI. Now you will see with L1 on, although in the simulation environment it's hard to track, but trust me that the results with the real data are in the paper. It can be downloaded from IROS 2020. And as I said, we went to study a little bit contraction theory to come up with nonlinear baseline controllers that can help us to navigate in cluttered environments. So control contraction metrics parameterize Lyapunov functions on the differential space. We get convex conditions for synthesis that makes it easily computable, and the Riemannian energy that's defined through the geodesic length serves as a Lyapunov function here and as certificates subsequently. So what we did, we extended it to have explicit disturbance rejection, and by then we were lucky. Marco Pavone was one of our collaborators on NSF robotics grant called Syndrome for last mile parcel delivery. And it was easy quickly to exchange ideas, get the right papers and collaborate. So we extended it to have explicit disturbance rejection and get tubes for control signal and state variables simultaneously. We got a simulation environment where to simulate it and to do the comparison study. And here it is. So here is that original paper. Jean-Jacques is also here with Marco. And this is the way we did the disturbance rejection and got... why doesn't it go? Okay, I have to hit the right places. So here is, we reduce the time of travel to 9.6 seconds from 13.9 seconds. And the tube sizes get reduced. So with this type of baseline controller, so naturally we are going to put now everything together. So we have contraction theory that gives us safety tubes with incremental stability properties, actually incremental exponential stability properties. We augment it with L1 adaptive controllers, and we add Gaussian Bayesian learner there, and we get some of the guarantees already in probabilistic sense. So if we put all this together, we get safety certificates in the form of tubes for this contraction L1 GP framework, which enables safety during learning. Here is the architecture, which is planar agnostic, and we can use any planar with it we want. And here is like some numerical data from a paper that was published in L4DC 2022, I believe, or 2021. If I mix up the year, sorry. From randomly initialized 10 trajectories, 8 would hit the balls. If we just use our L1 adaptive controller, it will go around because it's deterministic, it's conservative, it will rely on small gain theorem, Lyapunov, give us the most conservative safe path. If we do a little bit of learning, that Bayesian learner, it will help us to go in between the tubes safely with certain probabilistic guarantees. So this brings us to the framework of defining this distributionally robust adaptive control, where we can merge the language from both domains and enable more aggressive applications and have distributional robustness certificates. So what are we interested in? A general consolidation framework of machine learning and control must contend with a language barrier. They talk different languages. A prototypical machine learning pipeline can be described roughly like this. So you have data, you have model class that you choose, and you minimize this expectation, right, which we call empirical risk. It's an expectation over the training data that relies on the distributions that form our training data. These are empirical distributions given from past operations, simulations, and so on. What guarantees can we expect from the machine learned models? A trained model right? Optimized parameter set, learned model certificate, right? Which we call R. And it's referred to like model risk in machine learning literature. And the performance guarantees here are very much distribution dependent. And there are extensions to Wasserstein ambiguity sets around empirical distributions. So there's quite a bit of literature here. So using what machine learning can provide, how to ensure predictable and safe control. So the guarantees are now defined distributionally if we follow this framework, and not on finite dimensional vector spaces, but probability measures on them. Therefore, we need control architectures that satisfy a priori uniform guarantees on the space of distributions and can be applicable to general class of nonlinear systems subject to both epistemic and aleatoric uncertainties. So we look therefore into itostochastic differential equation, the description of general class of nonlinear uncertain dynamic systems. And the representation can be here done either with sample paths, trajectories, or distributions that you see around the sample paths. So there is incomplete knowledge of the vector fields, which are the epistemic and aleatoric uncertainties. So if I go forward, so the WT is a Brownian motion, we'll now quickly define it. So given the true system, XT is a strong solution of a stochastic differential equation, nowhere differentiable. WT is a Brownian motion, it's almost surely continuous Levy process. F mu is the drift term, that's the average mean behavior of sample paths, while F sigma is the diffusion term, which characterizes the randomness of the sample paths via correlated and state multiplicative injection of the Brownian motion given by WT. So looking into the true system, the uncertain drift term can be represented like a known component plus unknown component, matched and unmatched uncertainties. Uncertain diffusion term can be also decomposed into known component and unknown component. And we have noisy control channel here through UT-DWT. If we have only the drift term, we'll be back to nonlinear deterministic ODEs, right? Because the Brownian motion enters through the diffusion term. If I look into the true system and understand how these drift and diffusion terms are constructed, I will isolate a nominal system which has only the known components. But yet, I have to assume that there is a Brownian motion associated with the nominal system, and that these two Brownian motions of the nominal system and true system are independent. Otherwise, I don't have a good problem formulation here, a fair representation of the reality. So there is a distribution shift between the two distributions between the true system and the nominal system that we are interested in mitigating. And that has to do with these uncertain terms. Our goal is to apply our learned policy that's available to us through training data distribution and the optimization of the regressor that we did, and while applying the optimized policy to the true system to mitigate the distribution shifts, because the guarantees of safety and predictability that are defined on the training data distribution will not be valid for the true system. So what we do, we want to design a feedback augmentation here that we call pi A, that's the adaptive augmentation, so that the true distribution remains uniformly bounded around the nominal distribution. And this can be quantified in terms of distributionally, used for upstream distributionally robust planning and control. And we will measure the distance between these distributions through Wasserstein metric, which is a concept borrowed from optimal transport theory. It's a metric that preserves distance and shape. So if we want the Wasserstein distance between the true and nominal distributions to remain within an ambiguity set, and we want to be agnostic to the training data. So the ambiguity tube of distributions here, you see the green is the nominal system, red is the true system, and the red always remains around the green without ever leaving the blue. So we need some assumptions on the nominal system to begin with, right? So if I take out the diffusion term and the Brownian motion, I'm left with a deterministic system on which I want to have incrementally exponentially stability type of assumptions with its associated Lyapunov function as a certificate. So we assume existence of incremental Lyapunov function for the nominal deterministic subsystem that's used in this process. And the L1 adaptive controller has its three components, like we always said. It's the state predictor, adaptation law, and the low pass filter. So the key here is that we take the deterministic L1 adaptive controller that's designed around the nominal system in its deterministic sense and apply it to the true system that has these stochastic uncertainties that we talk about, these distributions, and we now analyze what would be the performance of this controller if it's driven, for example, by colored noise, right? So we retain the identical structure, architecture for L1 adaptive controller for nonlinear deterministic systems. It's stochastically now inherited through feedback that comes like color noise feedback injection through the Brownian motion. That's the real world. So we have a deterministic model from a textbook around which we designed a deterministic controller with all its certificates. And then we apply to the true system. We just acknowledge the true nature of the true system. So our predictor all of a sudden is perturbed by colored noise, and we need to give the guarantees in the space of distributions. So the feedback design remains in the standard state space, but the guarantees now we provide in the space of distributions or space of probability measures on the state space. So we do not assume unrealistic distributional feedback. Okay, it's the same controller that we have applied to Learjet web flow. Well, now we analyze what are its distributional guarantees and when can our certificates be valid. So here is the summary of the main result. I avoided putting a heavy theorem here. So what do we get? So if the initial, there is some bound assumed obviously on the initial distributions, and the bounds are proportional to the filter channel bandwidth and adaptation rate, or the sampling period of the CPU, like I said in the beginning. But we get three new constants that were not present in the deterministic analysis. And this C3 is what, if you remember, we said the pilot was saying there is still something there, three angles that were left. Now we found why they were left. And without doing this analysis, we wouldn't have recovered. So the key point in the proof that we use the transient bounds of L1 adaptive controller. We get the bounds on the P's Wasserstein norm in these inequalities. The term C1 is there due to unmatched uncertainties that will be always there in the real world. C2 is due to the independence of the Brownian motions, because I said that the nominal system in this setting have to have its own Brownian motion completely independent of the true system. And it's lower bounded by some constant which will never go to zero. It's not present in the deterministic system. The C3 term is due to noisy control channels, which is also an assumption of the real world that we have to meet. In the case when the Brownian motions go away, we're back to the deterministic scenario. We recover the L1 performance bounds that we had in deterministic setting because the 2 Wasserstein norm collapses to Euclidean norm. Here are some numerical experiments of this, right? So we will look into this angular rate of a quadrotor. In the absence of this controller, as you see, that the Wasserstein 2 norm just diverges and the distributions diverge. If we add the L1 adaptive controller, the 2 norm converges to a constant bounded away from zero. This is the C1 plus C2 plus C3. It remains bounded by 0.01 here, and so they never collapse. And here are the comparisons visualized in 2D when kind of in the absence of the controller they diverge, in the presence of the controller they come, and here is the visualization of the metric to 0.1. Here are lots of extensions coming up. So we can extend it to general Levy processes. We can do further experimentation of this controller with learning elements, because right now this was just the stochastic analysis of the L1 adaptive controller applied to real systems, but we can bring in the learning components here, this future work coming, to enable V and V of control systems with learned components in the loop. Distributional certificates, deep learned dynamics and controllers can be studied with this framework. And propagation of the robust data-driven certificates through the complete control pipeline for distributional robustness, for planning and control. And naturally, while doing all of this, we also try to fly something in the lab. We have students who are anxious to fly, so we have a custom-built quadrotor that's a PIXOC platform, samples at 440 Hertz. Here is when it flies over a big box for ground effects, and you see without the L1 adaptive controller it has significant instability due to ground effects. With L1 you see that small buzz that's always there. If we had not done the stochastic analysis, then would say just the solutions are bounded, but now we know how they are. This is the slosh payload. It's half-filled bottle. When it flies, this half-filled bottle, when it shakes, it introduces significant change of center of mass and everything. So the baseline controller here is a geometric controller, which is well known for quadrotors, and as it flies, it shakes up the water in it, and you see it slowed down motion to visualize the shake-up of the water now if you see as it gets close. And then it goes back to the nominal L1 adaptive controller to recover. And the errors are significantly reduced, right? So we go to the next one. It's a chipped propeller. And with a chipped propeller, there is significant thrust reduction. So it flies, it's almost about to crash. We turn on the L1 adaptive controller to stabilize it. And when we take off the L1 adaptive controller, it crashes. You will see it now. So how it goes into crash. And then we do 4 different chips, four different propellers. And with 4 different propellers, it's highly unstable because it's highly asymmetric. So when we take off the L1 adaptive controller, it goes into these unstable oscillations. And then we put on the L1, it gets back to stable hovering now. Then the next experiment is a downwash. Here we have a heavy drone flying on the top of the experimental drone. The heavy drone is in front of that poster, white poster, and the experimental drone flying under it. You see, we have also the PID controller that manages to damp out the oscillations with significant transients. And this is like the geometric controller alone. So with L1, we are kind of with better transients. We fly through small wind tunnel that was created. Here are tufts that blow away. You'll see how they blow away. So we fly through these wind tunnels that we make up in the lab to facilitate such experiments. And as you see with L1, we have again much smoother performance as compared to PIDs. Finally, we do asymmetric weight hanging, and these asymmetric weights attached to drones. Why doesn't it run? Okay. So the bottom left one will crash, and we'll now look into the data from all these experiments together. Here is the data, and let's look into the data. So these are the boxes. The pink box is the geometric controller. The green is the L1. The yellow is the PID. As you see, a few cases we have bounds just comparable to PID. But with L1, like all the bounds remain much closer to each other than with PID variates more inside the box. And in some cases, we are just significantly better than the PID controller. And this we are talking about very well-tuned PIDs. So all this performance is consistent throughout the experiments without any retuning or redesign of L1 adaptive control parameters. But as we said, right, if you don't do machine learning, maybe it gets really hard to face the communities and give all the answers. So we took the model-based reinforcement learning framework and tried to augment it with L1 adaptive controller. This is a paper accepted in ICLR this year. It will be presented in Vienna. Let's see what's the challenge here. So the challenge of using robust adaptive controllers with model-based reinforcement learning control algorithms are characterized by the fact that the robust RL algorithms learn models that are highly nonlinear. Parameters of the neural networks do not equal the true parameters of the physical system. Nominal models produced by this MBRL algorithm are not amenable to control tools. So the possible solution is to constrain the model structure to control a fine or linear class, but then it comes at the price of sacrificing the performance. So what did we do? We added a kind of model affinization block and the L1 adaptive controller. Very long paper with detailed proofs. I'm not going through this, obviously. The design requirements that we impose, that we cannot touch the high-level MBRL algorithm. It cannot be changed. It's industrial, it's innate. And no additional requirements from the high-level MBRL algorithm are taken into consideration. So the framework is to integrate an MBRL baseline model with L1 adaptive control and to show performance improvement for cases when the data was not seen or used during the training. So it's operated by on-the-need affinizing the learned dynamics and affinization along the control trajectories, and it's implemented on the affine dynamics, the L1 adaptive controller. Here are the comparison cases. We played with 5 different models that are common in this literature. It's the inverted pendulum, swimmer, hopper, walker, and half cheetah. And only in one case we were not able to show improvement. As you see, it's highlighted here by red. In all the other cases, we showed significant or substantial improvement to kind of justify the design. So performance is sustained with both aleatoric and epistemic uncertainties and in action and observation, in the presence of action and observation noise as well. The baseline MBRL algorithm that was used here is known as MetPro, so the citation is here. And finally, I want to do a little bit shameless advertisement of our center. Chuchu is a part of it, that's why she invited me here. So it's a NASA ULI effort, NASA University Leadership Initiative that spans over 5 universities and 2 industries. We have 15 co-PIs on the project. And we look into development of robust, resilient autonomy architectures for urban air vehicles, so-called flying cars. So the key thrusts involve control, path planning, machine learning, certification, V&V, and flight testing. And we're happy to have this collaboration opportunity with Lockheed Martin and Sierra Nevada Corporation that help us with some of the flight test solutions and also vision-based sensing solutions. So what do we want to do? So we started from the fact that we wanted to bridge the divide, but we also want to keep in mind the fundamental limitations. And why fundamental limitations? If I go back to 1989, when the first body lecture was done at CDC, Gunther Stein from Honeywell recalled the X-15 crash in 1967, which was one of the most successful flight test programs at NASA, but the pilot Michael Adams was killed. As the later analysis revealed at Honeywell, it's the adaptive control parameters that went into spin and the controller saturated, and it was tragic. So Gunther Stein made a very good comment in that presentation. If you haven't seen it, go, it's on YouTube, you can see. It says it's good for a discipline to have conservation laws. Conservation laws keep us humble. So in control theory, we know very well how to trade off performance for robustness, and that T plus S equals 1 is never going to change. My feeling is that in machine learning community, we still haven't found the conservation laws, right? And in machine learning, it's mostly one message: give us all the GPUs, all the labels, all the ground truth, we can learn everything. But it's not like that. So I had one student who was interested in looking into fundamental limitations for stochastic systems. He defended his dissertation last year, went back to China, unfortunately. He was just attracted from there with significant offers. And these are fundamental problems to keep always in mind. There are fundamental limitations that must be well understood before we deploy any solution involving or not involving machine learning on a safety critical platform. With that, I want to acknowledge my group of students, alumni, postdocs. It has been 20 years of research, or even more, involving many different outstanding people who have significantly contributed to this work. And certainly I want to acknowledge our sponsors, Air Force Office of Scientific Research, National Science Foundation, Army Research Office, NASA, and many other companies that have shown trust in us and have funded our work. But above all and everyone, I want to thank Test Pilot School at Edwards Air Force Base for giving us the real vehicles to deploy our solutions on the real vehicles and have this type of demonstrations for similar seminars. Thank you very much. If any questions, I'm happy to take.